Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, thank you, Andy, for warming up the audience so well, and thank you for an excellent talk. I shall change the subject a bit and talk about the past rather than the future, and tell a number of stories around the question: can computers understand their own programs? And I shall bring some witnesses to provide evidence that computers can understand their own programs, at least in a certain reasonable sense. And my main witnesses will be Alan Turing, whose picture you've just seen, Euclid, and Aristotle, since they happen to be what I studied at school and university. No, I need to turn on the...
Yeah, that should work.
Show completely.
Yeah. See. Yeah.
Oh, well done. Thank you. Computers are wonderful, aren't they, when you know how to press the button. I'm going to tackle the question by asking three relevant auxiliary questions and answering them first. The first question I'd like to tackle is, can people understand their own rational thought processes? And again, I think the answer that I will give you will be yes. And the evidence that I shall quote was already provided by Aristotle and Euclid. The second auxiliary question is, how can a program be understood? And here I shall call on Alan Turing. First of all, he is the inventor, pretty well, of the notion of a computer program, or rather a program-controlled computer, a general-purpose program-controlled computer, in a paper that he published in 1936. In a mathematical journal, and more recently in 1949 he gave the answer to the question of how a human being can understand a program sufficiently in the usual sense that he or she can answer questions about it which are at least plausible, convincing, and sometimes even true. And the third question I need to answer, what does it mean to say that a computer understands something? And here again I shall turn to Alan Turing, who in 1950 wrote a paper published in the British philosophical journal, Mind, on computing machinery and intelligence. The legacy of that paper is now the Turing test, for which there is an outstanding competition and prizes offered, and also, one might say, the origins of the study of artificial intelligence. So, impact. I think we can say all of the authorities that I'll be quoting have had impact. So, question number one, can people understand their own thought processes? Well, I'm going to talk about rational thought processes, processes of human reasoning. I'm going to omit a very important topic of inductive reasoning and concentrate on deductive reasoning. So I shan't be talking about learning or machine learning in the sense of machine learning, or the sort of discoveries that scientists make by induction, but rather the way in which people reason deductively from premises to conclusions. And the person who invented the idea, as far as we know, invented the idea of deductive logic, of setting out clearly the premises of your argument and step by step deducing consequences from those premises that are true of necessity, as Aristotle described it. That, I think, that is what I'll concentrate. That is what is due to Aristotle. Now, Aristotle was a polymath, and he published treatises on a number of subjects, which I've listed here. That's an unusually wide range of interests. He actually set up a school in Athens, the Lyceum, in which he took probably paying students to teach them those subjects. And his students wrote down a large number of his lecture notes, which survive by good fortune to the present day. He originated the three basic ideas of deductive logic. That logic is defined by giving a notation, just a way of writing down on paper a description or a denotation for each relevant concept that you want to reason about or reason with. And then you could also specify what the grammar of the judgments of your proof are going to be. So each line of a proof is going to be a statement or assertion or a proposition which follows from previous lines. It may be restricted to a particular grammar. And then the third thing is you give a grammar for each deductive step of the proof by showing a pattern according to which the conclusions, according to which a particular line of the proof can be shown to depend on previous lines of the same proof. And I shall describe how that happens. The particular form of grammar that was used by Aristotle in his logic was taken from natural language. And it's quite familiar to school children these days of how you can analyze a sentence into its parts and talk about the parts separately. So in ancient Greeks, Aristotle was one of the few philosophers who actually used letters to stand for parts of speech. So letters to stand for anything, actually, because the ancient Greeks had a problem with letters because all their letters stood for numbers as well. And therefore they couldn't invent algebra, which was quite a serious deficiency, I think. Anyway, in this particular case, Aristotle allowed a letter to stand for the subject of a sentence, let P stand for the predicate of a sentence, and then he permitted 4 grammatical ways of writing sentences of a proof, beginning with all, some, or no. Each of them contains a subject S and a predicate P. So here's an example. All S are M, all M are P, therefore all S are P. This is an example of a rule of deduction. If you want to prove that all S are P, then one way to do it is to prove the 2 premises of this deduction. That find some middle term, M stands for middle term, of which you are willing to prove that all S are M, and then using the same middle term, you can prove all M are P, and from those 2 previous lines in your proof, you can deduce that all S are P. Well, this particular pattern of deduction is very obvious, I expect. How many of you are familiar with the Aristotelian syllogism? Fine. Well, good, thank you. The various forms of the sentences were given abbreviated letters A, I, E, and O, according to the table shown on this slide, and the sentences beginning with all were labelled A, and in this syllogism, as it's called, this rule of inference, all the lines of the proof are of the form A, and therefore this was called Barbara because the letter A appears 3 times in the word Barbara. And it was important to Aristotle to it is important when you're teaching Aristotelian logic to have convenient names for each of these rules of deduction. Here's another rule with a pattern EAE, no MRP, all SRM, therefore no SRP. You can check any of these rules by drawing a Venn diagram. It's all just Boolean logic, but the point of the proof is that you can use these rules blindly in your proof without having to think out on every occasion, is this a valid proof or not? Here's a third one, radii. And there were some more. There were 24 of them. So it was rather important when this technique was taught in schools and universities that they all had reasonably pronounceable names. These names were invented in order to distinguish the 24 modes of the syllogism. In fact, it turns out that they are, of the several hundred possible triples of sentences that you can express in the Aristotelian grammar, there are only 24 of them that are valid syllogisms, and Aristotle found them all. Now, fortunately, logic is now a lot simpler than it used to be in Aristotle's day, and for the next 2,000 years thereafter, because modern logic has just one rule of inference, modus ponens, and a couple of, half a dozen axioms, perhaps I should say, or maybe a dozen. And it's much more powerful. We can prove much more from the logic than Aristotle could. This form of logic was taught in universities in Europe and the Middle East for 2,000 years. So if you're looking for impact, I would strongly advise you to settle for something a little less than 2,000 years. Aristotle showed the way, of course, but he's a difficult example to follow. Let's go quickly through. I think the important thing about Aristotle's proof, which he discovered, actually violates all common sense views about what makes a valid proof. The ordinary man in the street in Aristotle's day, and probably still today, would, if he's asked, what is it that makes a proof valid, will probably say, oh, that depends. That depends on who's doing the proof. If I like him, I'll accept it as valid, and if I don't like him, I'll reject it. Or it depends whether I like the conclusion or not. I'll accept the ones I like, I won't accept the ones I don't. The more discerning might say, well, it depends on whether the premises of the argument are true or not. Again, the answer to that is no. A perfectly valid argument can proceed from invalid premises. Of course, the conclusion won't actually be true, but the argument will be valid, as long as all the premises are presented in the argument itself. The only criterion for whether a proof is valid is the text, the syntactic form of the proof itself. And that was a great discovery, and it's still valid today. Now, it's because the validity of proof is a syntactic concept that it's very easy to check by a computer. Computers are very good at syntax, they can look at the way in which something has been written and check that it conforms to a pattern like that of the Aristotelian rules. Computers can also discover proofs by exploring all the possible deductions from the lines produced so far. A very inefficient way of doing it and very ineffective. A lot of research has been expended in Microsoft and outside to get computers to discover proofs a little bit more efficiently than that. And computers have recently been used to prove the four-color theorem and the Kepler conjecture, which are long-standing. I think I'll have to go on to my second question, or I won't ever get on to the third. How can a program be understood? The answer that I'm going to give was already known to an ancient Egyptian philosopher called Euclid. He was the person who first showed how to prove the correctness of a program. We know very little about Euclid. He was working in Alexandria in Egypt around 300 BC. Again, like Aristotle, his primary work, The Elements of Euclid, 13 books, which were studied and taught in universities throughout Europe and until the late 19th or earliest 20th century. And in some audiences, I find that a good sprinkling of people have actually studied Euclidean geometry. Anybody studied Euclidean geometry here? Yes, good. Not such large numbers as I get in Italy and Switzerland. They hold the record for. So, my claim that his elements presented a large number of proofs of geometric theorems, and most of them include a what's nowadays called a construction, a way of supplementing a diagram, drawing a diagram, which can be used to, a set of instructions for drawing a diagram, which can be used by a mathematician or a map maker, and in order to achieve a specific objective which is stated in advance. So his theorems, the constructions are written in a sort of programming language with assignments and sequencing, subroutines and parameters, preconditions and postconditions, and every one of them is accompanied by a proof of the correctness of the program. The geometry is based on 5 postulates, just 5 axioms, and I've put 3 of them up here. Notice that they start with the word to draw a straight line between 2 points. That isn't the normal form of a theorem today. That is, it assumes, the assumption is that you are able to draw a straight line between 2 points. And in any construction of a Euclidean proof, you can appeal to this postulate or axiom to ensure that it is possible to draw a straight line between any 2 points. It's actually a basic instruction of his programming language. There are a number of actions in his programming language, and one of them is to draw a straight line. His programming language is very like what we would call a graphics programming language today. Graphics programming languages that are used to write all screen manipulating programs are similar and based on the same set of basic commands that Euclid included in his language for constructions. He gives 23 definitions, some of which are mutually recursive. Some of them are actually concealing an axiom. It's not quite as rigorous as we have learnt to be today, but there were only 23 of them. And what he called 5 common notions, which he realized that the logic he was using to describe his constructions and prove their correctness was just a particular application of logic, and there were some logical principles which were applicable more widely to different applications as well. So he called these common notions, and they are still used today in the predicate calculus in reasoning about programs and other constructions. Now, then in book 1 he has 48 propositions, the first of which is called to construct an equilateral triangle with a given side. So again, his proposition is a set of instructions on how to do something. So the proof contains a number of steps, each of which performs one of the actions in his postulates, like drawing a circle around one end of a line. And it's followed by, a little bit faster, a proof that the construction which has just been drawn does in fact draw an equilateral triangle. We've got to prove that the 3 sides of this triangle are all equal. And so by convention we will mark equal lines by some symbol which is placed over both lines. The two lines shown on this slide that are equal are marked with the blue equal signs, and the justification is that the 2 lines are both the radius of the same circle with its center at the bottom left corner. And that step in the reasoning is justified by an appeal to definition 15. And of course the same argument applies to the right-hand circle, where the 2 lines are the radii of the right-hand circle. And now, using common notion 1, anything that's equal to the same thing or equal to each other shows that the 2 non-horizontal lines of the triangle are also equal. So all 3 sides are in fact equal. And that, I think, perhaps I could say is the first proof of any program that has ever been published. And it's such a beautiful proof that it's really well worth teaching to people even today. Right, Alan Turing. We're going on to our 3rd question. What's this? How does a human being reason about programs? Alan Turing discovered a way of doing this and published it in 1948. It was only rediscovered in 1980 that he had published this a paper. It was a talk to the London Mathematical Society. Now, when I first left working for industry, my first 8 years of my career was spent writing software for a computer manufacturer, But I got interested in the idea of programs, programming languages, and proving the correctness of programs. And so I want to spend my remaining few minutes in describing how Turing and I, and actually many other scientists, including John von Neumann, the co-inventor of the modern computer, and Bob Floyd and Peter Nauer, have all come up with the same idea, but I'd like to explain the idea in the context of Aristotle and Euclid. The Hoare triple, which a notation which I introduced in 1969, is written with in three parts: a P and a V and an R, and it's rather like a Euclidean proposition. If you want to ensure R and P is already true, one of the things you can do is an action V. So the meaning of that triple is when P is true, an action V ensures the truth of R. So it's a logic of actions rather than a static logic like Aristotle's logic, which just describes the current state. P and R describe the state of the world before and after the action, but the action V is an action that is performed and changes the real world, or some part of the real world. For example, the part of the real world that exists inside a computer. That's the part of the real world that most programs change, but the logic is actually independent of whether you're describing a computer program or a set of ordinary instructions, or maybe even a geometric construction. In a geometric construction, the state of the world, which is described by P and R, are the state of the diagram that you've drawn so far. If the diagram you've drawn so far has a certain property, then you can add, by action V, you can add some new line or circle to the diagram and ensure that R is true after you've added it. So here are some examples from real life. What you can do by turning the knob of your, yes, what is it? Of your radio. The second one is a geometrical statement about geometry and figures, and the third one is a statement about what goes on inside a computer. If the value of a variable x of your program is greater than 3, increasing the value of x ensures that x will be greater than 4. Not a very deep statement, but probably a true one in most computers. Now the rules of the logic that I have worked on for most of my life are very similar to Aristotelian rules. They have two premises and one conclusion. The premises here state that you can achieve your desired result in 2 steps. If you start in a state P, this is in the last line here. If you start in a state P, can you see that at the back? Okay. And you want to achieve R. This is the wrong. Yes, here it is. If you start in a state satisfying P, you want to achieve R. Perhaps you can do it in 2 steps, an action V1 and an action V2. If you can prove that V1 will ensure that an intermediate state S is achieved, and V2 can start in S, and when started in a state satisfying S ensures R, then you can conclude that the compound action, the program, V1 then V2, will ensure the result R. And you can do something similar for conditionals. If you have an action which will work only if some condition is true, and another action which will work when that condition is false, then you can form a conditional, which is a statement of your program which will achieve the desired result if the actions V1 and V2 achieve that result. And here is a loop, here is a rule that describes repetition. Now, how do we know whether the computer understands something? And the answer was again suggested by Turing, the Turing test. Who knows the Turing test? Oh, lovely. Well, I think the Turing test was all wrong. It was a nice idea, and I'm going to take the important thing about the Turing test, but actually change the construction of the test. Turing test imagines a conversation between a tester and a machine on arbitrary topics of human interest. I think the first example, the tester makes a statement, shall I compare thee to a summer's day? Why don't I compare her to a winter's day? And the computer has to reply, well, the winter isn't quite as nice as the summer, so who would be complimented by being compared to a winter's day? That's tough. But he did say that the computer only has to fool the human being for 5 minutes. And furthermore, the human being is just an ordinary person taken from off the bus. I think probably all of you would know some questions which the computer would really find hard to answer, and take a lot less than 5 minutes to discover that it was indeed a computer. And that's the most recent public competition of Turing tests. Actually, the examiners really knew after one question that this was a computer. And the only mistake they made in the whole test was to say that a human being was a computer. But when he was interviewed afterwards, he said, oh, I thought we had to pretend to be a computer. So perhaps... So let's take perhaps a more serious version of the test. We are allowed to examine the machine, but only on one topic. We can only ask questions about programs. So that's going to simplify the task considerably. And furthermore, the test can go on as long as is desired to establish the machine is not going to try and fool the human being, but the machine is going to try to help the human being to write a program or change a program that the human being wants to change. So the conversation is not going to be a sort of trick, an exercise in deceit, but a genuine attempt to collaborate between the man and the machine in the construction of a program. And the criterion of whether the machine understands the program is that the machine can give an answer to the majority of the questions asked and explain why the answer is correct. So they're willing to present their reasoning to the human examiner. And that, I think, is the way in which we test the understanding of our students. We set them examinations. It could be an oral examination or a written examination. And we judge their understanding of the subject. Well, it's usually only on one subject. We judge their understanding about whether they can explain what and justify the answers that they have given. So you ask a pupil at school to present their working, and now you judge their working, not just their answers, which is just as well, because most of the answers are wrong, and it's really the working that you're trying to judge. In the case of the computer test, we want all the answers to be correct. We really want the human being to rely on the answers being correct. Well, the word all doesn't apply to engineering. Of course, there will be mistakes, misunderstandings, and somebody will have to come in and correct the computer if it turns out to be wrong. The other important characteristic is that the answers are relevant and useful to the human programmer, and the human programmer can judge that. And so the eventual test is that the human programmer prefers to write programs with the assistance of the computer rather than by his or her unaided intuition, which is what the programmers use very largely today. So here are some typical questions that a human programmer would be interested in the argument in determining. First one, does the program contain a fault that makes it vulnerable to viruses or other malware? Can the program overflow its buffer, which was a known danger a number of years ago, which made software liable to viruses? If the answer to that is yes, then we want the computer to tell us in what circumstances that error will occur, and in general to generate test cases that exercise all the changes that have been made recently to the program. That's a very difficult thing. We don't know how to make computers to do that, but it's certainly what a programmer wants when making a change to a program. Can this change make the program slower? Are all the assertions made in this program valid? Or could the aeroplanes under control by the program ever collide? Some programs actually control the real world, and it's very important that they shouldn't fail. Now, I'd like to end with a quotation from J. Moore, as a colleague who's made remarkable contributions to the field. He believes and hopes that within 50 years, within his own lifetime, he will be able to implement a design automation system for software engineering, similar to the automation systems that are available now in many other branches of engineering, statistics, civil engineering, bridge building, aerodynamics, ship design. They're all done now with very massive computer assistance, but programming is still a little bit of a cottage industry. What J. Moore would like to see is that all serious programmers are using a programmer's assistance, not just in the programming, but in the analysis of problems, the design of the program, the architecture of the program, the actual development, programming, testing, delivery, and subsequent evolution of the program could all do with computer assistance. And that's also my vision for tomorrow. Sorry, not for tomorrow. I mean, my vision today for the software of tomorrow. It's this which I have made the strategic goal of my lifetime's research. Thank you very much.
Thank you, Tony. Tony. So we can take a couple of questions to Tony. Any questions?
So maybe I'm wrong, but there has been a recent progress in this direction. Computer system named Watson, who won the Jeopardy contest.
Yes.
So I don't know much about it, but could you comment on that? Is it relevant to this field? Can it help
Yes,
somehow?
there is a program that has played the game of Jeopardy on US television, which is a sort of general knowledge quiz, which really very expert human contestants have to try to beat each other. And on one of the sessions, a computer, Watson, was registered by IBM as one of the contestants and won. Now, I think this is a really remarkable achievement, and it is a form of test. It isn't Turing's test, of course, but it does illustrate very considerable progress towards achieving the Turing test. The way it was done was by what I would call inductive logic. The machine had access to a vast database of literature and facts and linguistic material, and when it got a question, it analyzed the syntactic form of the question and the vocabulary to try and find some sentence in this vast database that could serve as an answer to the question. Then it used a lot of heuristics to decide which answer to actually give. So, because making sure that the answers are relevant, sensible, useful, reasonable answers at all is quite difficult. But that would be the subject of another talk, because it's more about machine learning than about deductive logic. And great advances have been made in machine learning, particularly from vast amounts of data that are today stored on machines.
I see. Thank you.
Any more questions for Tony?
What do you think there is much that stands in the way of this 50-year goal? Do you have any idea of sort of what stands in the way of achieving that if we try to achieve it today?
Yes, nobody knows how to do it. I think that my view is that the achievement of the goal will require a rather large-scale collaboration, a collaboration in which academics can make very important contributions, but other contributions can be made by industry, but it's not going to be achieved by the single lone researcher. Computer science will have to evolve in the same way as physics and biology and other branches of science, that there's a much clearer and much larger, higher degree of collaboration between individual scientists throughout the world. And so I think, but at the moment, the culture of computer science is still much more the individual laboratory, the individual scientist, and it will take some time to persuade people that they're going to have to work together more effectively. I think it's happening slowly, but the other thing we'll have to do is to persuade the funding bodies that this is the new paradigm or a new paradigm of computer science research, that people can collaborate across countries and across continents to achieve a goal, the same way that the physicists do when they put up a satellite, or astronomers do when they build a telescope. This is done by a worldwide collaboration with hundreds or maybe even thousands of people contributing a small amount to it. So if you're happy to work in teams, good luck to you. There's plenty of challenge out there.
Thank you very much, Tony, once again.
Thank you.